driving forces. Okay. So we started this conversation on Friday. We were looking at membranes. We reviewed the structure of membranes. And we then started talking about what are some of the properties of particles that allow them to go through the membrane? What are some of the properties of the membrane that allow some particles through and not others? We talked about this idea of passive transport, which is, energy liberating, downhill, spontaneous. We talked about active transport, which is the opposite. So uphill, going against the passive transport, and is going to be requiring energy. We then moved on to speak more about these two forces, what we call driving forces. And just to kind of recap our discussion here, we said that a driving force is the separation of energy across the membrane that then creates this push or pull that wants to move particles in one direction or another, right? And that's the general description of a driving force. We then went on to talk about the chemical driving force, which was one of the forces acting on particles. This was based upon the concentration gradient, so the difference of the actual number of particles on either side of the membrane. If we had a higher concentration on one side versus a lower concentration on the other side, that was one of the driving forces. That's the chemical driving force that wants to bring those particles to equilibrium, or move them in such a way that they're equally distributed on either side of that membrane. And we illustrated that. We then began talking about the electrical driving force, and this is where we got to. So we introduced some terminology that's really important in understanding this electrical force, which is the difference between a cation, which is a positively charged particle, versus an anion, which is a negatively charged particle. And then we introduced this idea of the membrane potential. So the membrane potential is a force that is due to the distribution, the unequal distribution of positive and negative charges across the cell. We talked about the fact that it's referencing the inside of the cell. So when I tell you that the membrane potential of a cell is negative 70 millivolts, that means that inside of the cell is negative 70 with respect to the outside of the cell, or compared to the outside of the cell. So this was some terminology that we talked about introducing, and we got to really describing more about that electrical driving force, that second force also acting on particles to move across our membrane. So here we can see a good description of the electrical driving force, because we can see a membrane, our plasma membrane, that's separating two distinct fluid compartments. We've got the intracellular fluid, we've got the extracellular fluid. And then we can also see that there's a presence of cations and anions on either side, but they're not equally distributed. This is what that membrane potential is, that unequal distribution of charge. So if we had all negative charge on the inside and all negative charge on the outside, we would not have any potential to move any of these particles. There would be zero membrane potential. But because we have a separation of charge, because we have an unequal distribution of the charges, we've got more negative inside the cell, we've got more positive or more cations outside the cell. Because of that, we now have a force or a driving force, we can also call it a potential, to move particles across this membrane according to this separation of charge. So that's what the electrical driving force is, okay? The principles of the electrical driving force are that opposites attract and likes repel. So because we have a negative environment on one side of the membrane and a positive environment on the other side of the membrane, for example, a positively charged ion or a cation is going to want to go to the negative environment. So we've got this opposite attract and likes repelling, and that's the principle behind which we have the movement of these particles on one side or the other. The force is going to depend on two distinct factors. One is going to be the polarity of the cell. And when we say polarity of the cell, that's that distribution of charge, that unequal distribution of the charge. The fact that there's a negative environment inside and a positive environment outside. It's also going to depend on another factor, which is the charge on the particle in question. So remember, when we're speaking about these forces, we're really speaking about them acting on particle X. And if particle X has a charge on it, that will determine the direction of the electrical force. If it's a positively charged particle, it'll move in one direction, which is going to be towards the opposing side. If it's a negatively charged particle, it's going to be moving towards the positive side, whether or not that's in or out of the cell, depending on the state of the cell at the time of movement, okay? All right. So let's go ahead here to illustrate a scenario that would better explain this electrical driving force, this second force acting on particles. Okay, so we said that the electrical driving force depends on two factors. One is the charge on the particle in question. The second factor is the polarity of the cell. And now the polarity of the cell is also going to depend upon the state of the cell. And I'll explain what that means here in a little bit. So the second factor is the polarity of the cell. And that really means whether or not the inside of the cell is positive or negative. At rest, it's going to be negative, but we can also have this cell in an excited state where the inside becomes positive. So when we describe the polarity of the cell, we're really talking about the state of the cell. This can be rest, let's say resting, resting or excited, which is really positive inside or negative inside, okay? So that polarity of the cell is going to be whether or not the inside of the cell is more negatively charged or positively charged, or whether or not the outside of the cell is more negatively or positively charged. And again, that is going to tie into the state of the cell, whether or not the cell is excited, if it's a muscle cell or neuron, or whether it's resting, if it's at a resting state. So let's draw two cells here. Let's draw two different scenarios. We're going to draw a resting cell and then an excited cell. Oops. So here's our resting cell. And then here's an example of an excited cell. So let's talk about our resting cell first. So our resting cell, we know, has more negative charge inside the cell and more positive charge outside the cell. So we've got an abundance of negative charges. We'll talk about how that comes about a little bit later on, how we actually establish the resting membrane potential. We'll talk about that. But for right now, we know that the inside of the cell is more negative than the outside of the cell. So we've got a few positive charges inside and then much more positive outside the cell. And we can actually think of this as being an abundance or an excess of our cations. So we have an abundance of sodium, right? Sodium is a cation, it's positively charged outside the cell. And then we can also think of this as there being an abundance of anions, let's say chloride, for example, inside the cell. So the movement of our particle is going to be outside the cell for a positively charged, outside the cell for a negatively charged anion like chloride, right? It's going to try to go to the positive environment. So chloride is negatively charged. There's an abundance of negatively charged ions inside the cell. And so the electrical force acting on chloride is going to want to move it towards the positive environment, which is on the outside of the cell. And so this is what we mean by that electrical driving force. It's going to move the particles according to one, the state of the cell. So where is there a more positive environment? It's also going to move according to the charge on the particle. So because it's a negatively charged particle, and because the outside of the cell is more positive, we're going to try to move chloride outside. So there's a force acting on chloride trying to move it out. Alternatively, the force acting on sodium would be trying to move it inside the cell. For the exact same reason, right? We have an abundance of negative charge inside the cell. Sodium, is a positively charged ion. It's a cation. And so it's going to want to get to the negative environment inside the cell. So this is our first scenario of a resting cell. And let's actually describe the membrane potential here. So the membrane potential is -70 millivolts. And we describe that the membrane potential simply means that inside of the cell has a negative excess or a negative charge overall when compared to the outside of the cell. Okay. In an excited cell, our membrane potential becomes drastically more positive. So this would go all the way up to, let's say, +60 or so. So +60 millivolts now means that the inside of the cell is more positive with regard or in comparison to the outside of the cell. So in a rested cell, we have a flip-flopping of the state of the cell. So the inside of the cell becomes more positive. Oops. So it's going to have an abundance of cations. And then outside the cell is going to have an abundance of anions, so very few cations. And then very few anions inside here. So if we're thinking about, again, looking at the force acting on our two particles, again, if we're thinking about chloride, where do you think chloride is going to want to move in an excited cell? So I'll give you a minute to kind of predict the answer here, and you can share either in the chat or just say it out loud. But where do you think chloride is going to want to move in an excited cell? Okay, excellent. I'm seeing some chat responses here into the cell. That's absolutely correct. So because chloride is a negatively charged ion or an anion, it's going to want to move into the cell where we have the abundance of positive charge. And then, as you would also probably imagine, sodium being a positively charged ion or a cation is going to want to move in the opposite direction where we have the abundance of negative charge outside the cell. Okay. And so this is what we mean by the electrical driving force. Okay, it's that force acting on a particle that's caused by the charge of the particle as well as the polarity of the state. And the polarity of the state is really a reflection of the state of the cell. The polarity of the cell is really a reflection of the state of the cell. Okay.